So I'm here just to talk a little bit about stuff that I'm getting more and more involved in. But I have to say that a lot of this heavy lifting at CSA Global has been completed by Dennis Arney and Rob Mackey. And we brought Eric Grunsky in, who has a brain far superior to mine, for a lot of the number crunching. All right. All right, so why are we all here today? Why should you care? Essentially, there's a problem with data. I think of myself as a scientist. I love data. I guess maybe the problem is, how do we manage that? How do we make more meaningful interpretations from that data set, right? It's very easy to get a whole multi-element data set and look at copper and gold, for example. But how can you better inform yourself using all of the elements after quality control? And there's also many, many sources in data sets like stream sediments, like soil samples, many sources of signal that are mixed together. And we're the geoscientists that have to pull that all apart and claim where the next best drill target is. We're looking for the sulfide source, the mineral source of chemical signal, and we want to strip out the lithology, we want to strip out the superficial effects like scavenging organics, material like that. So we want to optimize our data sets using everything we have, all of the variables we have in that data set. So I'll just jump right into some examples and some maps here. It's not really a short course, but I want to really showcase some of the products and some of the interpretations we were able to derive from the Northwest British Columbia Geoscience BC work. So this is the general area of the study. It's a small study, just a little bit bigger than the country of Denmark. So just toss that into it. But it's a good data set of fairly good spatial coverage, geologic variants, and mineral deposits. So you can see we tried to reduce the variability as much as possible. So we kept it to the green. Where's the laser? We kept it to the green domains here, which essentially are the larger terrains of the Stakenia, Quinellia, and Cache Creek terrain. You should be able to see that. Some of the figures later on may be a little bit small in these projectors, so what I wanted to highlight here is the diversity of mineral deposits. If you plot up all of the min-file occurrences, you get a huge swath of showings and occurrences along the southern edge of this Bowser Basin, which covers the Stakenia terrain and impedes exploration. You don't get any real min-file occurrences in the Bowser Basin. It's not really prospective, so you'd have to drill quite deep to get through it. But there is stuff underneath it if you want to get to that point. And then along the north and the west side, obviously, is the Golden Triangle. It's just a prolific area of metallogeny here. So the yellows are epithermal, so the Toodoggone area is going to be highlighted. Comess through Lorraine and Mount Milligan in the Quinellia terrain will be highlighted. But this region of the Golden Triangle here actually explodes in all of the data, and that it did in the original data as well, back since the 70s, so it's quite an obvious target. All right, I just threw this up here to show all of the data points that we were working with. You'll notice some of the samples are missing. Those just simply represent protected areas, parks, stuff like that. But there's pretty good spatial coverage. It works out to about one sample every 13 or so square kilometers. But it's not perfect, as we'll see later on. And most of this is Aqua Regia ICPM SES data from recent Geoscience BC funded reanalytical programs. And we added a catchment layer to this. Those of you who know me know I'm a GIS nerd, I guess you would say. So integrating all of this GIS data, the spatial data, into your geochemical sample data point is huge in the optimization of this, first and foremost. And like I said, Dennis Arney's been really kind of paving the way, establishing this with these huge regional data sets in an open source fashion, I guess you could say, with Geoscience BC projects, and I'm carrying along the torch here. We were able to use these catchments developed by the BCGS to attribute dominant lithology per catchment, and we're also able to use the surface area, the catchment size later in our refinement of the products. One of the biggest features, I should say, of the optimization, data optimization here was the validation of stream sediment locations. Many of the locations in the existing data, the precursor database were wrong, so if you snapped them to the nearest stream and did this catchment analysis on your own, you would have developed the wrong catchment potentially if there was enough bifurcation in the streams themselves. So I threw this in here to kind of as an example of a fairly simplistic way to look at things. You know, something that probably would have been done or has been done many times over. You could do raw element percentiles and just plot that up. I believe that's how the RGS published the data originally. It was just percentiles in gold, and you can go off on your way. So here you can just normalize a bunch of elements that you deem suitable. This is something I just threw together. But you can see it it highlights the golden triangle very well up through the GT gold area we saw earlier this morning. Red Chris porphyry deposit up here. But you also see the Bowser Basin is quite a, let's call it a high background of these metals as well, right? I mean, down at the southern earlobe, it almost looks like Africa actually, doesn't it? The southern earlobe of the Bowser Basin stratigraphy is quite high. Is that material shedding off into the Bowser Basin, right? How do you filter this out? I probably wouldn't fund a drill program there unless you had favorable stratigraphy, right? So these are things that were unoptimized, right? So there is a reason, there's a rationale to look closer at these data sets and look for more subtle signatures that the previous people may have missed. All right, let's just jump into some examples here. First up is principal component analysis. This is kind of the core of what we've developed here. What we've been doing for a little while is exploiting the idea that PCA can identify correlation. Essentially, it'll mix and translate the data in a sense that maximizes variance, and it'll determine which of your variables express the largest amount of variability in the database. This has been used in genomics extensively, neuroscience, anything where there's a lot of data, but more specifically where there's a lot of variables as well, and the brain just can't visualize that alone. One of the other benefits of this is after your quality control and you threw out the elements or the variables that are not really of any worth, or they're all below detection or half below detection, all the variables that are good to use, fit for purpose, it uses all of those in its results, right? And it spits out a product that we can understand a little bit easier. I just threw this up here. If you haven't done a PCA before, this is one example of a preliminary result you will get. Eigenvalue, which is kind of a sense of variance, variability, how much of an impact it has in the major data set. You're going to have the most significant here. The first principal components along the x-axis, the first and second PCs, they account for the largest amount of the variability in the data set. So this is what we're going to be focusing on, but I will highlight a few of the slightly less significant principal components that it's up to the geologist to determine what they actually mean and how valid they actually are, right? So we'll ignore everything else below here just for a functional basis. And looking more closely at a principal component, we can see all of the elements that are compiled into here. So it does a combination of all the elements, and the only thing you really need to worry about essentially is if these ones on the far extremes, the highest and the absolute lowest, the ones in the middle don't really play a big role in this component. So you look for clustering of these elements, and you, as a geoscientist, you ask yourself, does this make sense? What does this mean? What could this mean? PCA doesn't tell you which sources. It doesn't split them out exactly very well. If there's a confusion, a mix of sources that have the same elements that play in there, it won't tell you that. You have to use that as, you have to use additional you have to use additional data to evaluate. How much time do we have? Okay. So this is just a quick summary. There's no real rational way to actually visualize what the principal components is showing you. So I've put it on this 2D projector screen here. All of these principal components are mutually orthogonal to each other. That's just a function of the stats and how all the maths works. But I wanted to split it out here to just kind of quickly summarize all those scree plots I showed earlier. So you can see here, generally the largest variability in your geochemical data sets is going to be your primary lithology, mafic, felsic. Those are very different, right? We all know that. So usually you can split that out in the first principal component, but this is very interesting around the golden triangle from SK down to Dolly Varden. It seems that these pathfinder elements, cadmium through mercury there, they versus the mafic or sodic mafic signature, that controls the largest amount of the variability. We'll get into some of these other ones a little bit later on, but let's get to the pictures here. So this is the first principal component. You can see, as I said, it's heavily weighted by these pathfinder trace metals, right? And it lights up. This is just straight PC1, gridded, percentile gridded, and you can see the main golden triangle area, the prolific KSM Brucejack, for example. They light up above anything else, but the entire Bowser Basin is outlined. I don't know if you can see this, but I tried to put a dark line in that outlines the Bowser Basin limits as defined by the fairly detailed BC Geological Survey, and it matches it incredibly well, right? There is arguably, I guess you could use the human brain and observe a bunch of patterns that may not mean anything, and the structural geologist may say, hey, maybe I can see some linear patterns there. Whether or not that makes sense, I mean, that's an added bonus if you can prove that, but it does show you that Bowser Basin highlights very well. So you can use this product or a combination of these products later on to combine them to reduce different areas that are less significant in your geological or geochemical model. There we go. Let's go into principal component 2. This is the mafic felsic. So this is the major rock type difference that I was mentioning. So you can see the uranium, lanthanum, thorium combination here of PC2 highlights and is spatially associated very well with felsic intrusions along the coast plutonics suite here, as well as some intrusions in the Quinella terrain north of Mount Milligan, between Mount Milligan and Lorraine deposits, and perhaps the best indicator of the Bowser Basin stratigraphy here is this opposite end of PC2, which is cobalt, magnesium, nickel, scandium, chrome. For any nickel geologist out there, you know those are key indicators for your prospective rock types. But in this case, it tends to highlight the Bowser Basin incredibly well, and this can be very useful later on. I'm not saying that this probably isn't a Sudbury hiding underneath here, but you have to use the brain to filter out these signals. PC4. This actually was surprised. Actually, it had tellurium, copper, bismuth, moly, and some magnesium, which seems to be a metal, a copper deposit signature, right? So you look spatially, and it does have an association with Galore Creek up here, some of the region of the Golden Triangle, not terribly well, but in some in the Quinella terrain north of Lorraine. But I mean, this association has to be further evaluated by the geoscientist. One of the more interesting themes that I came across when I joined CSA and started working with Dennis and Rob was their idea of residuals, element residuals against the principal component. I kind of was skeptical at first, but the idea is if the principal component now becomes your proxy for a process or for a lithology, for some kind of domain lithologically, then you're using that. It's no different, essentially, perhaps to regressing or leveling to known lithology, right? So this is what they were trying to exploit. So just as an example here, graphically, here's just, backwards. Here's the zinc. This is the center log ratio of the raw zinc value as plotted. And you could say, okay, well, maybe a lot of this is just highlighting different sediments in the Bowser Basin here. So if this is principal component 3 here, and you can see a great correlation or a great relationship, apparent relationship with the zinc value to the principal component, and you say, well, let's see exactly what all these values here, what is all this excess, excess zinc content related to this principal component. So this is an example of what you may end up receiving on the bottom end, and it's up to you if these are valid or not. It could go for any element you're looking for. It's up to you if these are valid, if it works. You have to really integrate it with your additional geoscientific data to decide if you want to add it to your targeting toolbox, essentially. But this is something that has been used and compiled into a final weighted sum model for a target. So the Geoscience BC work, we published weighted sum models, which is a single value, a single index that you can plot spatially. You can do additional statistics with, which is our best guess. It's let's call it heavily supervised. We pick or we use all the knowledge we have for existing deposit, what its minerals should be, what its chemical composition is, what trace elements it should have, and you combine all those together with the weightings you choose and the rankings you choose, and use the weighted sum model, which ILGAS has, for example, very easily, or you can just look up this paper, and it does some interesting maths, and it gives you a value. I mean, this is a very iterative process. This was a very iterative process to refine these, and the overall goal was to see how close you could fit these models to known deposits, known locations, known samples in this case. So it's getting closer to what Adrian was talking about, but and like I mentioned before, we're integrating the catchment to GIS layers here, but to show a map of actual data, right? If you get an anomaly, if you get an actual sample point that looks prospective, where do you go from there, right? You can't just pretend as if it's going to behave in the same way as the inverse distance weighting grid. You can't go in all directions, right? There is natural processes at play here. So the diagram on the right is the catchment map that we came up with our porphyry copper weighted sum model. You'll notice in brackets it says dilution corrected. Unfortunately, it takes a lot of work, and nature just doesn't comply. It doesn't allow us to take samples that define the exact same catchment region or the exact same catchment size for each sample. So you kind of have to account for that. So to do that, I don't actually, it's quite a specific way to actually do it. I believe it's the linear regression of the original weighted sum model against the square root of the catchment area. If you want those details, it's all published in the Geoscience BC report. But the diagram and the result is, let's just put it here. The diagram and the result is this curve. So you end up peeling off the most significant values from the vast numbers of small catchments. Because reasonably so, you don't expect a small catchment that happens to be cutting through a mineralized vein to be treated the same way as a catchment that's 10 times larger, with more sediment being funneled in and diluting the mineral signal. So I have time for independent? 3 minutes. Okay, let's say this is pretty quick. So independent component analysis is pretty new for us anyway, but we thought we would apply it. It's similar in certain ways to PCA, but it doesn't really care about correlation and making that lozenge shape figure that you're potentially used to seeing in PCA. It cares about recombining all of the variables into linear combinations that finds unique linear combinations that represent mutually independent processes. So in this little diagram here, you have mineral source, lithology, mineralogy source, and secondary processes perhaps, and it tries to do linear combinations of all of the elements that you want to put into it, that are valid to put into it, and it comes up with unique features in data space that I have represented like such. This isn't entirely accurate, but you can see how it doesn't really care to have orthogonal components, but it tries to split them out, whereas this is more of a single lozenge-shaped PCA. Let's go. I'll just skip that. We ended up computing all of the PCs, so this is what we've ended up with, essentially, and I peeled out a few of them. This component number 2 here highlights the late volcanic centers, the Mesopeak and the Adziza complex, extremely well, right? Maybe you'd be able to use this in the future to peel out, to reduce those samples in your database to say, you know what, those are noise, we don't want to factor those too much, right? You really can't go to town with these without some skepticism geologically and really evaluate it with the known data that you have to make sense of it. But the best part of all of this is you're using the data to show you things. You're not introducing errors such as the quality of mapping that's been done. 1 minute, okay. So inverse 2, Bowser Basin. I'll just quickly flip through these. These are all in the report. Bowser Basin highlighted again, so this indicates process in mineralogy. And if you're a nickel guy or a Warriorite explorer, you'll have nickel target rocks just within this one principal component, or this one independent component. Skip that one. And we did fly onto random forest, which I think Adrian touched on. This was kind of an experiment, let's call it. It's a vote system, so instead of one decision tree, you have test data, you have a huge number, it's a brute force decision tree, and it's a voting system, majority rules in this case. And so this is based on known occurrences and catchments over known occurrences, right? We pulled out a alkalic porphyry copper classification and highlights right over Galore Creek very well, Mount Milligan area. It kind of tends to overestimate the Quinella terrain maybe a little bit, but this is all fairly independent. I should note that the training data set included all known alkalic porphyry deposits in this case, right? Plus 100 additional catch samples with known mineralization in that catchment. And then the results here excluded all of those, right? So this is just straight learning from that known data set. And it doesn't include any of those known locations in this data set here, in this result. And this quickly for epithermal gold. Maybe there's some noise there. Let's say there is some noise, misclassification, but the Tutagon area in the northeastern location highlights excessively well. So perhaps there's a catchment that's in some open ground there. And I think that's essentially a summary there. There's promise here, and I think there's room to merge into some of the more machine learning, but I think healthy validation with known geologic data or additional geologic data is extremely valuable and necessary here.